All right, hello everyone. Welcome to our first lesson on finance equations and the mathematics of money. So this unit we're going to be doing a lot of work with both compound interest and monetary problems that you may be already familiar with if you've taken pre-calculus, but we're going to also dive deeper into the meanings of things like retirement accounts, amortization tables, um, if you took accounting, you may be familiar with mortgages and amortization tables, so we'll uncover that a little bit more here as well. Um, I thought I'd start this with a fun little picture here. This picture you see here in front of you um, is a lot of money. And each of those stacks, by the way, um, most of that is US money, all the giant stacks of green, that's all $100 bills. This was seized in a drug bust not that long ago. I want to say 2017 or 2018. And if you want to take a guess as to the total value, think about um, you know how much this is actually worth. I'm not sure what some of these other currencies are down here. I believe the red is either British currency or Mexican currency. The blue, I'm pretty sure, is Canadian, and there's some other different currencies down here as well. Okay, so how much money do you think is in that pile? You can always pause the video, write down a guess, and I'll tell you in a few seconds. Okay, this was seized from a Chinese-Mexican drug kingpin, and the total value here is somewhere between 206 and $226 million. Uh, that's a huge amount of money to have lying around in cash. And certainly, um, when we do interest calculations this unit, as you can imagine, hard cash like this is not the result of interest calculations. That's certainly for sure. Um, Hilariously, I can also uh, tell you that this is how much money was left over after this particular drug kingpin went gambling in Vegas, where he supposedly lost $175 million. So this is like half of what he used to have. It's crazy. Perhaps we can generate this kind of money using the math that we learn in this unit. So in this chapter, our goal here is to look at situations involving simple and compound interest, right? Um, Again, things you might have done in pre-calc, um, but we're also going to go a little bit more than that because it turns out that not every account can operate the same way that you've learned before. So the problem with compound interest is that you put the money in once, and in order for that calculation to work, you have to not touch it. And for most normal people, that's hard to do. You can't just put $5,000 into an account and just leave it for 20 years. Well, some people can, and those are the lucky ones. But on top of that, even the lucky ones, they're not going to operate the account like that. They're going to keep adding to it. So there's another type of calculation that we can do that's called the systematic savings. And the systematic savings is one that we're going to look at, I believe, section 3.3. And then finally, there's loans. And so things like how to tell how much money you have to pay for a car if you have to take out a loan for 5 years. And what's the difference between 5 years and 6 years on a loan? Um, and also things like what happens if you make extra payments. So, like one common thing that people tell you when you go to get a car or a mortgage is if you can make extra payments. And the reason why is the money for extra payments like takes away from the amount that you borrowed. We call that the principal, but no interest is calculated on that, which is really important, and that saves a lot of money in interest. And one common thing that you're going to see in this unit is that if you make for a house, right? A house is normally a 30-year loan. If you make one extra payment every year, just one extra payment, let's say, your mortgage payment is $1,500 and you make one extra $1,500 payment. So you make 13 payments in 12 months. That 13th $1,500 payment has zero interest applied to it. That purely comes off the balance of the loan. And what will then happen is it shrinks not just the interest, it shrinks everything. And you end up paying the loan off in 22 years, which is really pretty amazing. That just by making one extra payment a year, it actually knocks off over 8 years worth of loan, which is, and 12 times 8 is 96. So um, another way to think about it is you are making 22 extra payments, but saving 96. So definitely to your benefit to do so. So we're going to talk about all of that stuff in this unit. Okay. Um, so the way though that we're going to approach all of our calculations, no matter what kind of formulas that we use here, is we're going to have formulas with lots of variables. We're going to have to substitute numbers into those variables, and then we're going to have to solve those equations. So before we can get into any of the actual monetary stuff, um, this particular section that we're going to look at first is all about solving um, the equations and understanding the principles of how to solve these equations. So yeah, we're going to learn about the properties of exponents and things like logarithms are going to come up as well. Oh, don't give me that look. I know you're rolling your eyes at the computer right now. Guys, most of you, again, if you've done Algebra 2 or Pre-Calc, you've done logarithms, you've done properties of exponents. It's fine, I promise. Now, here's the good news. Um, because this is an application-based course and not, say, Pre-Calc, um, we're not going to really dive too much into the theory. In fact, I kind of assume that you've seen some of the theory already, um, but we'll develop just the little bits that we need, right? I'm more concerned about the application of it and knowing like, hey, not just like all the little different properties of a logarithm, but um, like what does that logarithm mean at the end? And why did we use it to solve this particular problem? So those are the things that we're going to do. And a lot of it's going to be calculator based. Logarithms work out messy, so most of this is calculator. Okay, so here's a few examples here, and this one's is already pre-written for us, which is kind of lovely, um, because we already know what positive exponents mean, right? Okay, so positive exponents, 2 to the third power. 2 times 2 times 2 is 8, or 3 to the fifth. 3 times 3 times 3 times 3 times 3. And that's 243, if you're counting. Now, negative exponents are going to come up in this unit as well. So one thing is that a negative exponent is a reciprocal of the positive exponent. And I'll just write that here, reciprocal of the positive exponent. And so if 2 to the third is 8, 2 to the negative third is 1 over 8. And then 3 to the negative fifth is 1 over 243. They're never negative, and that's important. Exponent, when you take any real valued exponent of a positive number such as this, you're never going to get a negative answer. Um, and that's important because money, in the sense that we're going to deal with, will never be negative. Um, even money that we owe. So we're always going to treat money as a positive quantity. Because think about it this way, even with like a loan, right? You may think, oh, I have to owe money. Yes, but somebody has that money, right? And that somebody is going to eventually, in the case of a loan, is going to be the other person, not you. They're going to be getting your money, but the interest is going to work the same way. So we're always going to treat money as a positive quantity. Okay, so let's look at some of the basic properties of exponents that we're going to be using. Um, so the simple properties that we should know and be able to work with is something like, first off, let's say we had a squared times a to the third, and that's going to equal a to the fifth. And a times a times a times a times a. That's five a's all multiplied together. So this is going to come up in situations where if you have a amount that's in an account for 2 years, and the same amount is in the account again for 3 years, or um, like you take the money out of one account that's had interest for 2 years, and then you put it in a similar account for 3 years, it's like it was in a single account for 5 years, right? I mean, just makes sense. Subtraction rule is the opposite. Like if multiply makes you add exponents, and dividing a to the 10th divided by a to the 6th is going to equal a to the 4th. You're just going to subtract those exponents. And that's just the case of the way that things cancel. Okay, some other rules that are going to be important here. Um, Power of a product. So here's a situation where if you have something like AB, say to the fourth power, is equal to a to the fourth b to the fourth. So what this is saying is that exponents basically distribute across multiplication. Um, and so this is a situation where like if you have um, multiple terms all being multiplied together, whatever that exponent is can be applied to each one, and their parentheses can be gotten rid of. Um, the one thing you have to be careful is it does not distribute across addition. So if you have an expression like this, say you had a plus bc to the third power, you have to leave that alone. The only way to multiply that out is to actually like write it 3 times and use distribution on it. So this does not fall under power of a product rule. This does. So I hope you see the difference here. Okay, the one particular rule that's going to actually be probably the most important of all of them is the product of a power rule. And that's this one. That says that if I have a single exponent with two separate powers attached to it through the use of parentheses, so two powers acting on the same base, then those exponents get multiplied. This is extremely important because of, if you recall with compound interest, how you have um, sometimes interest being applied more than once per year. So where this is going to come up the most is in situations where like you have an account where the interest is calculated every month. If the interest is calculated every month, um, and or even same thing with a loan, right? The interest is calculated every month, and then you make a payment every month. Let's say you have a 5-year loan. Um, the the loan is not really treated as a 5-year loan. It's treated as 12 times 5 or 60 months. So this would be like saying like, you know, a if I have something that's in for 5 years, but it's compounded 12 times a year, interest is going to be calculated 60 times. And that becomes supremely important because then that actually changes the effect of all the numbers and realizing that you have a smaller interest rate applied more often and you're going to get different results there. So this rule applies a lot when we're talking about finance. Other things that I think are important to keep in mind as well, some extra things. Um, Always good to remember that a to the first power is equal to a. Um, Here, think like if you have um, an amount of, so like for example, if you have 1.03 to the first, that's going to equal 1.03. And what that means is like if you have an account that gains 3% interest, and that's what the 0.03 will represent, and it's in the account for 1 year, your account is 3% bigger. I know, duh, right? And a to the 0 power is equal to 1. So this means if you have money that's in the account of for no years or no time, it's got a multiply factor of 1, which means your money hasn't grown. But it also hasn't shrunk either. Again, pretty obvious cases there. And I'll separate that out as number 5. Okay, so those are some important properties that we'll need to know. Okay, the other main thing that's important for us to know is how to undo an exponent. So when we solve an exponential equation, um, we're going to have two kinds of equations. Um, One where x is in the base of the exponent like this, and then one where the x is in the exponent. So let's start with the case where x is in the base. So x to the fifth equals 32. Now, you might be able to guess what x is. Um, just in case you were counting, 2 to the fifth is equal to 32. So x equals 5. But how could we do that out, right? So remember that we need an operation that can turn that x to the fifth into x to the first. Well, how can I do that? Um, well, I know that x to the fifth divided by x to the fourth is equal to x to the first, um, but that would require us dividing by something that we don't know its value. So that doesn't work. So the only other way to do it is with x to the fifth raised to some power is equal to x to the first. And so what does this have to be to get those to multiply together to get 1? Well, it looks like we're going to have to use a power of 1/5. And so what this means is that if we have an expression and we wish to get rid of that exponent, we're going to use a power of a reciprocal to that exponent, regardless of whether it's positive, negative, decimal, or anything. Um, we're not going to use a radical or a root like you might have done in pre-calc because um, sometimes those have funky things like if the root is odd and then you might get double answers and extended value. We're not going to worry about fancy equations. We're just going to say we have this operation, we have a way to undo it. Let's figure out what x is. So what I'm going to do is I'm going to take this equation, x to the fifth equals 32, and I'm going to raise both sides to the 1/5 power, like that. And on this side, these cancel. I'm left with x, and then I'm left with 1/5 power. Now, again, we know what the answer is, but let's look at the calculator to be sure, right? So I'm going to turn on the calculator here, and I'm going to do 32 exponent 1 divided by 5, and boom, the answer is 2, exactly as we expect. Okay, now let's take a side note here, and I have to warn you of something. Parentheses. Now, this particular calculator I have has a fancy print to it where it separates the exponent up the way that you would normally see it on paper. Not every calculator is as lucky. So many calculators, as I'll show you, we'll go switch this to classic. Okay? Um, Many calculators, what they'll do is they will have 32 exponent and then it's all in one line. If you have a calculator like this, you must put the exponent in parentheses. And we get the correct answer of 2. If you don't do that, you will get a much different answer. Why? Because um, the calculator will always do the exponent first, and it will always do exponent before division, unless the division is in parentheses. So remember, it just follows PEMDAS the way that we would as well. So folks, make sure you use parentheses, because I swear if you don't, I will bring the wrath of THANOS down on you. I mean it. Okay. And as I've said before, with this unit, parentheses become kind of like, you know, public enemy number one here, if you will. If you don't get 100 on the test, it's probably because of parentheses. They're that important, and they're that much of a sticking point. So I will be yelling at you about them constantly. Okay, so same thing here. Let's take a look at the operations needed to solve for y, right? Um, all right, so let's do some operations. So without much ado, we're just going to jump right into solving it. So we're going to do 1.31. We have a 19th power. 1 plus y to the 19th equals 1.31. So I'm just going to take that, and I'm going to raise both sides to the 1/19th power. And I'll put it in parentheses. So I'm actually going to use my calculator in the classic mode, um, just so that you guys get used to seeing the parentheses. And we get an answer of 1.0143. Okay, so here's the thing. When we do calculations like this, we're going to want to carry the calculations as much as we can. When we get into the money problems, we're actually going to want to do 8 decimal places. That does seem excessive, yes, but we'll have good reason for doing that later on, and it actually does produce um, some very tight rounding um, with some of the equations that we do. So you'll carry your calculations to 8 decimal places, um, but give a final answer at 2. For our purposes here, while we're learning, we'll just use 2 decimal places for now. And so this is about 1.01. Um, and so 1 plus y is equal to 1.01 because these exponents canceled out. And so I can subtract 1, and I get y equals 0.01. Okay, yeah, lots of decimals here, right, folks? Okay, but that's the way this is going to go. Okay, now let's look at the other case. Now, I suppose we could do one more practice um, before we go on. So a situation like this, let's say I had, say, 20 parentheses, um, 1 plus x over 6 raised to the power of 7. And this is going to equal, mm, let's give this a number of, oh, I'm just going to throw something out there, say 73. Okay. All right, so how would I solve this equation for x? Okay, let's just jump right into it, right? Always start from the outermost operation. The outermost, or the last operation being done here, is not the exponent, it's the multiply by 20. So we're actually going to divide both sides by 20 to start. And 73 divided by 20 is going to be, oh goodness, so 73 divided by 2, so 3 point, wow, I'm blanking out on this one. It's late, folks. 73 divided by 20 is 3.65. Okay, so 3.65 is equal to 1 plus x over 6 to the 7th. Okay, take both sides, 1/7 power. So in my calculator, you can just hit the exponent key and it produces answer, open parentheses, 1 divided by 7, 1.203, you can round it however you want. Let's do 1.20, just for our sake here. So 1 plus x over 6 equals 1.20. Subtract the 1. Uh, X over 6 equals 0.20. Multiply by 6, and you get x equals, oh, look at that, 1.20. Didn't plan that one, but there you go. Um, and it works. So I'm trying to look over the, so yeah, this sounds about right. Okay, and so there we go. Okay, let's see what we can do from here, right? So this situation solves for x. We use this reciprocal operation when the exponent is a number that we need to cancel out. What about this situation? What happens when the variable's in the exponent instead of the base? Now all of a sudden our reciprocal exponent no longer works. We can't do like 1/3 to the 81st power. Be nice if we could do that, but unfortunately that doesn't work. 2 to the x equals 47. Ooh, trial and error. Um, so here we know that x is going to be 4 here. 3 to the 4th is 81. But in this particular case, this isn't a whole number, right? So 2 to the 5th, oopsie, 2 to the 5th is equal to 32. 2 to the 6th is equal to 64, so that's going to be somewhere in the middle. 5.5 maybe? Not sure. 1.07x equals 2? Okay, let's figure this out. Okay, so in 1614, a Scottish landowner named John Napier published a book detailing how to solve these equations. Um, his book became kind of the gold standard of mathematics of this type for over 300 years. It wasn't until the advent of calculators in the 1950s, 1960s, that what he called the logarithm book became really out of style. Um, we now have a button on the calculator called log that allows us to solve these sorts of problems. So here's kind of a quick crash course in how logarithms work and how to solve this many different types. Okay, so the log button that's actually on the calculator is called the common logarithm, and it's based on base 10. Why? Because 10 fingers, 10 toes, things like that. Okay, so the common logarithm is notated as log A. And I wrote that in red, just kind of illustrate that. It's equal to the exponent that, when applied to 10, is equal to A. In other words, if I have, let's say I have the equation 10 to the x power equals A, right? So if I have this equation, I want to know what value of x. Here's a good example. Like if I have 10 to the x equals, say, 23. Now, we know that's not a whole number, some decimal, right? So what a logarithm does is it implies that x is equal to the logarithm of 23. So that's the definition. Now, that doesn't exactly tell us what that number actually is, but we're going to call it the logarithm of 23. And that's the number that 10 raised to such power equals 23. So how does that get calculated? Very carefully. Calculus and trial and error and infinite sums, blah, blah, blah. The calculator has a fancy bunch of things that it does to calculate this, um, all of which definitely involve a good background in calculus, but we're not worried about that. What we know is that it does come up with the answer. And if I pull up the calculator and I turn it on and I clear and I do log 23, close my parentheses, that number is 1.3617274. So it gives it to many decimal places. And so if I were to write that to 2, 8, or however many, that number is correct as far as you want to take it. Okay, um, so that's what we're going to do. We're going to rely on the calculator to create these. Okay, so let me show you. Um, we know that 10 to the first equals 10. So that means that the reverse of that is the log of 10 equals 1. Log of 10,000 is going to be 4. Um, the log of 1/10 is -1. So here's the thing. If you recall before, remember how we said that exponents, when you apply an exponent to a number, even if it's negative, it produces answers that are positive. That means that logarithms are only defined for positive numbers. So let me say this nice and loud. Logs of negative numbers are non-real. Um, Basically, as far as money concerns, such answers don't exist. Um, they do not produce a real sum of money. If you find yourself throughout a problem, you get to a negative number and you attempt to take a logarithm of it, it will fail, and you'll know you've made a mistake somewhere. Okay, so let's try a few of these, right? For the first one, you just simply have to take a log of both sides, right? Until you get x equals log 38.1, and that value is log 38.1, 1.58. Okay, what about this one? So here I'm going to explain a little bit about what happens with algebra. So when you do a logarithm, the way that we perform the logarithm operation is we'll take both sides and I'll do a log on both sides. And so we have the operation of log 10 to the power of x over 12 equals log of 0.422. The log and the 10, because the log is in base 10, cancel out. And you're left with x over 12 equals log of 0.422. To solve this for x, you just have to multiply by 12. And so x equals 12 times log of 0.422. And rather than doing the log of 0.422 out first, I'm just going to do this all in one shot. Now you could write it out first. You could do log of 0.422, write it down, and carry that all the way through if you want. Does not matter. Log of 0.422. Unlike trig problems, like sine, cosine, tangent, log does not get affected by like degrees, radians, nothing like that. There's no extra settings for it. It's just log. Negative about 4.5. So x equals approximately negative 4.5 in this particular situation. Okay, so that's really how these logarithm problems work. Um, Now there's one more thing we have to come up with, and you'll notice these equations have an exponent or base of the exponent of 10. Obviously, not every problem is like that, right? Okay. And if we wanted to solve the equation 3 to the x equals 15, which is an equation that I showed before. Now, the world doesn't just revolve around powers of 10, so what do? We only have this one log available to us, and that's a base 10 log. So I can't just apply it to any base. So I can't just say, you know, log 3 to the x equals log 15, right? I just can't do that, right? And it doesn't quite work that way. And So this doesn't cancel. I'm stuck, right? Not really. So there's a trick to this. We can use it. But we're going to develop, this is going to be the one little piece of theory that I'm going to show you, okay? So let log of a to the b power equals x, okay? Um, so I want to know if there's a different way that this can get rewritten. Okay? So let log ab equals x. So here's what's going to happen. The first thing I'm going to do is I'm going to raise this with a power of 10. And so I'm going to say 10 log a to the b is equal to 10 to the x power. So by doing this, I'm now treating both of these as exponents. Well, guess what's going to happen? The 10 and the logarithm, even though they're in opposite places to where you'd expect them to be from the last problem, they still cancel because they're still opposite operations. And so you're left with a to the b power equals 10 to the x power. Okay, now you may wonder how that's going to actually affect us. Okay, now here's the trick. I need to find a way to get rid of this a. So, or to change the a so that it's no longer a base. And the way I'm going to do that is by multiplying through with a log a term. So what I'm going to do is I'm going to put that in the exponent. I'm going to do a to the b times log a equals 10 to the x times log a. I can do that because I'm just multiplying the exponents by log a on both sides. Um, so this totally works. And why does this work? Because of the power of property, right? Because of the power of a product rule. So I can just simply taking both of these quantities and applying a log a exponent to both sides. But here's the thing, by doing that, right? I can now doing that, I can remove the parentheses and I can re-exchange these terms. And so now I have a to the log a times b equals 10 to the log a times x. Huh, that's interesting, right? Why would I do that? Okay, so now what's going to happen is now I'm going to look at this side over here, right? Now, at first, you realize, well, if I just cancel that out again, I'm just going to be left with a, right? No, a to the log a is different because the log is base 10 and this a is a base a. That doesn't actually cancel, but on the right side, it does. The 10 base cancels with the logarithm, and I have a log a times b equals a to the x power. And what does this mean? I'm going to now move this back over here. Because the a's are the same now base, I've converted the base of 10 into a base of a. And what that has now done um, is I have now said b times log of a is equal to x. Huh, how wild is that? And so it turns out that x was equal to log a to the b power, but then that's also equal to b times log a, so that these two expressions are equal. And what we now have proven is that log of a to the b power is equal to b times log of a. The exponent of b gets converted into a multiplication thanks to the logarithm. Now, that is pretty cool because what that does is it pulls the exponent apart of a to the b. So watch what happens here. So log of ab equals b log a. So if I attempt to apply that here, so what I'm going to now do is I'm going to say log of 3 to the x equals log of 15. But this exponent now can get shuffled over to the front thanks to this property. X log 3 equals log of 15, and now I can divide by log 3. And I get x equals log of 15 divided by log of 3. And in my calculator, I can do that and I get log 15, close parentheses, divided by log 3, close parentheses, 2.465. Oopsie. Wow. Oh, right. Wow, that didn't work. So 2. Wow. Okay. I need to shuffle my pen around. 2.465. This is called the change of base formula. And so it says, and so what it says is this. The log base b of a is equal to log of a divided by log of b. And this b here is for us to say that like it's a log of base 3. So another way that we can write it that probably also makes, if you've never seen logarithms before, a good way to write it is so now we can write this in the general case, is that if a to the b power equals x, and actually I don't even, because I want to keep the b, I want to keep the basis b. So if b to the x equals a, then x equals log of a divided by log of b. That's your big rule. Okay, and so that's what we're going to use to solve all these logarithm problems. All right, let's give it a try. Okay, so let's just pick a couple to solve, right? All right, so I'm just gonna write a couple things and let's see what we can do. So let's say I had the equation say 50 times 1 plus let's say x to the power of let's say 12t. Oops. Wow, I didn't want to do that. Let's change that equation up a bit. Okay, so let's say I did 1.07 to the 12t power, and that's going to equal, oh, let's do 75. Okay, so how would we solve for t, right? Okay, the first step we're going to do is we're going to isolate this term here. So we're going to do, we're going to subtract from both sides, or sorry, divide from both sides, and we're going to do divide by 50. And so we'll have 1.07 to the 12t power equal to 1.5. Okay, so now we're going to do a log of both sides. Because the log is a different base of 1.07, okay, what we're essentially going to do is we are going to take the log of both sides, but then divide by the log of the 1.07. And so I'm going to say 12t is equal to log of 1.5 over log of 1.07. And then that is going to be equal to log 1.5 divided by log 1.07, almost 6, 5.9928. And then all we do is we simply divide by 12. And so we get um, t equals 0.4994, about 4994. And there we have it. So that's how we're going to use logarithms to help solve these equations, okay? Um, so that's kind of just one quick example of how we use logarithms, go over some of the functions and formats of everything. Um, don't want to make the video too long, so I think I'll leave it here with a couple good examples. We can always try a little bit more later on, okay? Um, so again, just think about using the change of base formula and how it applies um, in any situation. And if it makes sense here, it'll make sense in even the hardest problems, okay? Have a lovely evening, and I will see you guys in class.